Alright, so in this video, this is a video for our lab, our Orifice Sizing Lab that we're going to be completing remotely. We can't, since we can't access the flow meter run, we're just going to be doing task 1 here in the lab is the only one that we're going to be doing. So we've got some information here. We've got a screenshot. This is a screenshot from one of our flow computers, a Flowboss 103. I don't know if it says here, but the software that we use to connect to it is called Rocklink 800. And this is a screenshot from that. So in the lab, this is a popular flow computer used out there. What I've done is I've stuck a orifice plate in our meter run and recorded some values and stuff from 2 screens. So this is the first page. Part 1 also is on the second page of the lab. Here there's another screenshot from the Flowboss, and there's a table here that we want to complete. So this table, we're going to be inputting some values into Blackboard from this table. The full table, here's the full table. You can see the full table right here. So molar mass I've given here, and let's just stop for a second here. Sorry, piece of information I needed to grab here that I didn't have handy was the meter run. We're not in the lab, so we can't get this information off the meter run, but I'm going to write that in right here so everyone has it. The internal pipe diameter on our orifice run, so the internal pipe diameter, it is 49. 49.2506 millimeters. So we need that information for doing some of our calculations. So I wanted to give that to you. And so the items here that we need to input, into our into Blackboard is all of these items here: the density, mass flow, and so on. So I just wanted to show you kind of how to navigate and find some of the variables that you need to calculate this stuff here. So for the first one, for our density here, for number 1, the first item, we will be calculating that from the formula that we were using in the orifice sizing presentation. So I believe that was yes, it's the standard density. So that we're looking for there. So that formula that we're gonna use is this guy right here to calculate that. So we need some variables. Actually, one variable, this guy right here. I need to point out where we find that. And I think that I've given to you as well right here for our molar mass of air. So that should be pretty easy for you to figure out. But I'm not going to do the calculation for you. That's something you have to do on your end to figure out our density at standard. So the next item is number 2 here, is our mass flow rate. So to get that information, what I wanted to point out here on the lab, right here it talks about, for determining mass flow, the flow rate shown is standard meters cubed per hour. And the flow rate that they're talking about, there's the one right up here in meters cubed per hour, which is on the screenshot that I took. So it would be this one right here that you need. So based on, once again, on the orifice sizing presentation that we did, we should now know how to figure out what our, and actually some of the valve sizing stuff that we did as well, same procedure to figure out our flow rate in kilograms per hour. Yes, right here. So to answer that question, so that's where we get that information. Meter run I gave you, you don't need to get that off the meter run. And then the flowing temperature, so number 3, that item, if we go back to our screenshots, here are all the values, the 3 measurements that are being made: differential pressure at the top, dP, static pressure, which is like the line pressure, upstream, and notice how it's in gauge pressure, and then the temperature right here. This is the temperature, so it's pretty close to room temperature that the air was at that was flowing through our meter run. So that's what was flowing through our meter run, was air, and that's where we're going to find that information. So we need to input that value. It's a pretty easy one for you to do. And the thermal expansion of the carbon steel, which is the pipe, and the stainless steel, which is the orifice plate. Alpha PE stands for primary element, and alpha P is just the piping, primary element being the orifice plate. So we'll need those because we need to calculate this value right here. So what we're following is we're not using our program in our calculator here. What we're doing is we're proving the values, the formulas that were given in that orifice sizing presentation. So we're just going to back up here. We haven't opened that yet. I'm going to back you up to the presentation. All the way back to slide, oops, one too far. Slide, I think this be like slide 4. It's just missing it down here. It should be, I think, a 4 here. We're after this value right here. So we have this value, that's the one that I gave you, that's that 49 millimeters, and you'll need to determine this value from the formula above to calculate our D value right here. We're going to need that in the end. We're going to need that to figure out what our orifice plate size is, I believe, if I remember right here. I'm just thinking back, but anyways, let's just go forward back to that slide to see what the next item is we need to determine. So that was item 4 that we were just looking up. That was the internal pipe diameter. Next is the Reynolds number, number 5. And so there's a Reynolds number calculation in the slides that we're going to use. Right here, it's our D value. So we should be able to plug in our mass flow rate in there. That's why we needed to calculate our D value at flowing conditions. You can see right here it says at flowing conditions, because we use it to calculate our Reynolds number. The mass flow rate, pay careful attention to these units, hint hint. You might need to do a unit conversion here. And also this right here is important. We need to be able to find that. So I'll go back to the screenshot to show you where to find absolute viscosity for calculating our Reynolds number. So let's go back to our FlowBoss screenshot, and I believe it's the second page here. Viscosity is right here, and it's in centipose, which is basically the same thing as a millipascal second. So be careful with your units there again. Millipascal seconds, let's just see here. Yes, this is in Pascal, so we'll have to do a conversion there as well. So we should, based on the orifice sizing lecture, if you did that, watch that video, you should now know how to get that into Pascal seconds so we can get the correct Reynolds number value. So back to our checklist here. Sizing factor, item number 6, SM. So there's a formula in our slides for that as well. And it's this one right here. So once again, mass flow rate, make sure your units are correct. The big D, make sure your units are correct. This is in meters, not millimeters, so make sure you do that correctly. Differential pressure, check your units. And density, check your units. So these two items, density and differential pressure, I need to point out where you'd find those as well on these screenshots. sorry, there's a lot of screens to go through here. Maybe I went one too far. Right here. Differential pressure. So this is what the differential pressure was flowing through the orifice meter run when we had that unknown orifice plate in the run. And our density at flowing conditions right here is given. So this is the density at flowing conditions, right? Because we calculated the density at standard. This here is the density at flowing conditions, because we do have pressure above atmospheric here that compresses it and it increases the density of our air. So that's why our density of our air is that value right there. So we need that for figuring out our meter sizing factor. If I just go back to that slide right here, and that should give us all our values now for figuring out the sizing factor for our differential producer. So we'll go back. Item number 7 that we need to figure out here is the beta approximation. So we're not going to be doing the iterations and stuff here. That's why I wanted to kind of just exercise using those formulas in the PowerPoint presentation rather than using our calculators and proving that they work to predict the correct orifice plate. So let's find that. The beta approximation. And it's going to be right here. Calculate beta approximation. So from that, we need to look at our Reynolds number. So once we calculate the Reynolds number, it's going to tell us which of these two equations to use. We just figured out our meter sizing factor, so we can plug it into the correct equation and solve for one of the values, right? So this is dependent on our Reynolds number, so we need to make sure that we get that right. So we shouldn't have any issues now with calculating that beta approximation. And now, instead of iterating and doing all that, we don't care exactly about how precise we're being. The reason being, we're trying to predict what size of orifice plate is in the line. Well, it's saying what size you recommend, but it's really what we're doing is predicting the orifice plate that I had installed in the line. And you can see our options here. I give you all the options because these are kind of the standard sizes, so it has to be one of these sizes that's listed here. And what we're going to be doing here is putting in, we're going to be applying this beta approximation to calculate our orifice bore that's in the line there. So if I go back to that slide with the, oops, right here. So this here is where we calculate the bore of the orifice plate. So we're going to be using our beta approximation value that we just figured out, the size of our inside diameter of our piping, and then the thermal expansion factor that we calculated as well to figure out the orifice plate at 20 degrees C here, and then entering that in right here for item number 8. So hopefully that guides you and gives you makes it a little bit clearer on how we're going to complete this lab. Once again, the other parts of the procedure aren't going to be done because we do not have access to the equipment. If we had access to the equipment, we would also be putting in another unknown orifice plate in and predicting it as well. So hopefully that helps, and all of these values here are going to be inputted into Blackboard to verify. So I'm going to get you to use at least 4 significant figures for all of your answers. Yeah, so you should be good to go.